First of all, I'd like to thank the organizers, Professor Gyotek Jin and Fajon Lee, for inviting me to this conference. And I'd like to talk about the cable gamma polynomial over knot. First, I explain what is the gamma polynomial, and we define the PQ cable gamma polynomial over knot. And in the section 2, by applying the 2Q cable gamma polynomial, we give sharper lower bound of the braid index and the arc index of Karnaugh knots. Okay? In the final section, we show that the 3 cable gamma polynomial is invariant under mutation. Okay? Let me start. Yes. First, I explain what is the gamma polynomial. Roughly speaking, the gamma polynomial is the common zeroth coefficient polynomial of the Honfly and Honfly PT and Kaufman polynomials. Okay, so I explain the Honfly PT polynomial and Kaufman polynomial. Okay. The Honfly PT polynomial is an invariant of an oriented ring satisfying the following scaling relation. The Honfly PT polynomial of the unknot is equal to 1, and we have for scaling triple L plus L minus L0, we have this relation. Okay, here scaling triple is 3 oriented rings which are identical except these parts. Okay. And Kaufman polynomial is also an invariant of an oriented ring satisfying this scaling relation. Okay. The Kaufman polynomial of the unknot is equal to 1, and for scaling quadruple d plus d minus d0 d infinity, we have this relation. Okay. Here, scaling quadruple is 4 oriented ring diagrams which are identical except these parts. Okay. And here 2 times nu is equal to the rise of d plus minus the rise of d infinity minus 1. Okay. Anyway, the Honfly PT polynomial and Kaufman polynomial of an R-component ring is presented by the following. Okay. And this Pn is a Laurent polynomial of the variable y, and this Fn is the Laurent polynomial of the variable a. Okay. And it is known that the zeroth coefficient of Honfly and Kaufman coincides. Okay, like this. And the polynomial P0 and F0 is a Laurent polynomial of the variable minus y square. Okay. So by putting x equal to minus y square, we call the polynomial the gamma polynomial. Okay. And namely, we consider this equality. For example, the Honfly, the gamma polynomial and Honfly PT polynomial and Kaufman polynomial of the negative Hopf ring is like this. Okay. This part is P0. This part is F0. Okay. And this case is a figure 8 knot case. This part is P0. And this part is F0. And this is gamma polynomial. Okay. And we reviewed the Conway polynomial and Jones polynomial. Yes. It is known that Conway polynomial is contained in the Hon-Fry PT polynomials, like this. Okay, so this P is Hon-Fry PT polynomial and nabla is Conway polynomial. So we have this relation. Okay, and the Jones polynomial is contained in the Hon-Fry PT and Kaufman polynomials. So we have this relation. This. Okay. And also the gamma polynomial is also contained in the Hon-Fry and Kaufman polynomial, so we consider this relation. Okay. Next, I explain how to calculate the gamma polynomial over naught. The gamma polynomial has the following scaling relation. Okay. The gamma polynomial of the unknot is equal to 1, and we have this scaling relation for a scaling triple L plus L minus L0. Okay. Here mu mu is this value. Here R plus R0 is the numbers of components of L plus L0. Okay. And the gamma polynomial has a special property like this. Let L be an R component ring and LKL be the total linking number of L. Okay. Then we have this equality. This property is very important. So by applying this scaling relation and this property, we obtain this special scaling relation for knot. Okay. Knot case, we L plus and L minus is also knot, but L0 is two-component link. So we apply this proposition, this two-component link. So we obtain this part. Okay. So it is very easy to calculate the gamma polynomial. For example, we can calculate the gamma polynomial of the figure 8 knot. This is the figure 8 knot. Okay. And by applying the scaling relation at the crossing, at this crossing, by crossing change, we obtain this k minus, but this k minus is equivalent to trivial knot. The gamma polynomial of trivial knot is equal to 1, so this is okay. And by smoothing, we obtain this two-component ring, and we can check the linking number of this component ring is equal to -1. Okay, and each component is trivial and trivial, so we can calculate the gamma polynomial of figure 8 knot like this. Okay, this part equals 1, this part equals -1, and this part 1. Okay. Next, we define the PQ cable gamma polynomial over knot. Let P is positive integer and Q are co-prime integers. And let KPQ be the PQ cable knot over knot K. Okay. For example, this is the 3-4 cable knot of the figure 8 knot. Okay. Then we define the PQ cable gamma polynomial as the gamma polynomial of KPQ. Okay. Of course, this is an invariant of K. Okay. Anyway, we consider this this polynomial. And in a similar way, we can define the Hornfly case and Kaufman case, Conway polynomial case, Jones case, like this. And it is known that Conway case is not interesting because there is a formula of satellite formula. So this is not interesting. And Jones case is related to the volume conjecture. So our interest is this case. Okay. And these two cases also interesting, but the calculation is very hard. So I try this case. Next section, we are by applying the 2Q cable gamma polynomial, we give sharper lower bound of the braid index and arc index of Karnaugh knots. First, we review the braid index. Every knot is presented as a closed braid. For example, figure 8 knot, we can deform the figure 8 knot like this, and we can see that figure 8 knot has this braid presentation. Okay. But anyway, the braid index of a knot K is the minimum number of strings needed for K to be presented as a closed braid. Okay? So, closed braid, always closed braid gives a upper bound of the braid index. So, we want a lower bound. Okay? And it is known that MF, the Morton-Franks-Williams inequality gives a lower bound of the braid index, okay, by applying the Hornfly PT polynomial. So this is the Morton-Franks-Williams inequality, okay. And the gamma polynomial is the zeroth coefficient polynomial, like this. So we have this inequality, okay. So, by using this inequality and this inequality, we obtain the Morton-Franks-Williams inequality of the gamma polynomial, like this. Okay. Of course, this inequality is weaker than this inequality, but we consider cable case. So, anyway, okay. And it is known that we consider Karnaugh knots. It is known that Karnaugh knots have the same Hornfly PT polynomial, like this. Okay.
So what is a Karnaugh knot?
This is Karnaugh knot. Okay. And this part is n full twist. This part is 1 full twist. Okay. And this case, minus n full twist. Okay. And this is Karnaugh knot, Kn. Okay. And okay, yes. So the Hornfly PT polynomial of the Karnaugh knot is always this value. Okay, this polynomial. So we see that the span, y span is the maximal degree minus the minimal degree on the variable y. Okay, so we see that the y span of the Hornfly PT polynomial of Karnaugh knot Kn is equal to 8. Okay, 4 and minus 4. Anyway, yes. So by applying the Morton MFW inequality, we obtain this lower bound of the braid index of Karnaugh knot. But this is always 5. Okay, so this lower bound is not good. Okay. Next, I show that two-cable gamma polynomials of Karnaugh knots. Precisely, two one-cable gamma polynomials of Karnaugh knots. Okay, like this. So important is this part. The span of the two one-cable gamma polynomial of Karnaugh knot is like this. So this depends on n. So this is good. Okay. So by applying this polynomial, we obtain sharper lower bound of the braid index of Karnaugh knot, like this part. Okay. Original case is always 5, but we obtain sharper lower bound, n plus 3. Okay. Okay, I explain the proof of the lower bound. Okay. For any knot k and any coprime integers p and q, we have this inequality. Okay. This is very natural inequality. Okay. Yes. Well, we just consider the parallel version, p parallel version of the k, closed braid k. And yes. And this inequality is MFW inequality. Okay. So we obtain by using this and this, we obtain this inequality. Okay. In particular, we obtain this inequality. Okay. So we apply this inequality, we obtain this lower bound. Okay. And okay, in this talk, I omit the upper bound. So, okay. But anyway, by applying gamma 2 polynomial, we give a sharper lower bound of the braid index of Karnaugh knot. And I have a question. Yes, this case, n equals 3 case. Our theorem says n equal to 3, the lower bound is n plus 3, upper bound is 2n plus 1. So lower bound is 6 and upper bound is 7. I don't know which 6 or 7. And I calculated the two-cable Hornfly PT polynomial by using Kodama's knot program and Kanenov's scaling relation of the two-cable Hornfly PT polynomial. Okay, but we see that the two-one cable Hornfly PT polynomial gives the same lower bound of the two-one gamma polynomial. So I don't know this 6 or 7. Okay. Next, I explain the arc index of Karnaugh knots. This is a joint work with Fajon Lee. And we review the arc index, arc presentation. An arc presentation of a knot is an embedding of K in finitely many pages of an open book decomposition of R3, such that K meets each page in a properly embedded single simple arc. For example, this is figure 8 knot. And we can deform this knot is like this, okay? And we see that this this book, this book has 6 pages. Okay, and we can see that single simple, properly embedding single simple arc like this. Okay. Well, anyway, and it is known that every node has an arc presentation. So we define the arc index of a node K as the minimum number of pages needed for K to be presented as an arc presentation. Okay. Yes. We always know our upper bound by using figure, but we don't know the lower bound. And it is known that the Morton-Beltram inequality gives a lower bound of the arc index, okay, by applying the Kaufman polynomial like this. Okay. And the gamma polynomial is also contain the zeroth coefficient polynomial of the Kaufman polynomial. So we have natural inequality like this. Okay. So by using this inequality and this inequality, we obtain the Morton-Beltram inequality of the gamma polynomial like this. Okay. And it is known that Karenov nodes have the same span. Okay, same span of the Kaufman polynomial like this. So we obtain a lower bound of the arc index of Karenov node like this. But this is also not good. Always 10. By using the 2Q cable gamma polynomial, we obtain a sharper lower bound of the arc index of Karenov node like this. Okay. And okay, I explain the proof of the lower bound. For any node K and any integer P, there exists an integer R with this condition such that this inequality. Okay. Yes. Okay, this inequality.
So what we have but brain is very easy.
Yes. Yes. Maybe Fajan only talks later.
Okay.
Okay. And by the Morton-Beltram inequality, we have this inequality. Okay. Yes. By using this and this, we obtain this inequality. In particular, we have this inequality. Okay. Yes. And it is known that for any odd integer q, we have this equality. So by using this and this, we obtain this sharper lower bound. Okay. Okay. Final section. I show that. Three. Okay. We consider cable gamma polynomials of mutant nodes. Okay, we review mutant node. For a node with a two-string tangle R, like this, Positively different knot obtained by replacing R by a tangle obtained by rotating R by 180 degrees is called a mutant knot. For example, in this case, we consider this mutant knot. Conversely, first we consider this knot, then we obtain this mutant knot. Okay. This mutant pair is very famous. This is called Kinoshita-Terasaka knot and Conway knot. And it is difficult to distinguish a mutant knot pair. For example, the PQ cable Conway polynomial and PQ cable Jones polynomial and original Honfly and Kaufman and 2Q cable Honfly and 2Q cable Kaufman polynomial cannot distinguish any mutant knot pair. Okay, so of course, gamma and 2Q cable gamma cannot distinguish any mutant knot pair. Okay, because we have this relation. Okay. But it is known that the three cable Honfly PT polynomial distinguish a mutant knot pair. For example, Kinoshita-Terasaka and Conway pair. Okay. So our interest is this question. That 3Q cable gamma polynomial distinguishes a mutant knot pair. But this answer is no. Okay. The 3Q cable gamma polynomial cannot distinguish any mutant knot pair. Namely, let K and K prime be a mutant knot pair. For any integer q with this condition, we have this equality. Okay. Next, I explain the proof of this theorem. Let DG be a diagram of K. DG is this. We may consider diagram of K. Okay. Okay. First, we set the axis x, y, z axis like this. Okay. Z axis is this. Okay. This means yes. And yes. This is a diagram of K. Okay. So K prime has one of diagram of dgx, dgy, dgz. Okay, one of them. Okay, gx is a tangle obtained by rotating around x-axis. Okay, like this. And gy is this. Gz is this. Next, we consider cable diagrams like this. Okay, here small g is twisting part. Okay, twist part. And g tilde is the three parallel version of tangle g. Okay. R tilde is the three parallel version of tangle R. Okay. And this diagram also similar way. Okay. And putting tangle Q is like this. Okay. This means this part. This tangle, we put this tangle Q. Okay. So this diagram is equal to this diagram. Okay. But And we see that this diagram is equivalent to this diagram. Okay, this diagram is equivalent to this diagram, and this diagram is also same. Okay. So our goal is to show that these equalities. Okay. And we see easily that if we have this equalities, then we have this equality. Okay, because z rotation is composition of x and y rotation. And we have this lemma. If we have this equality, then we have this equalities. Okay. Yes. Okay. And okay, d tilde q is this diagram, and we can deform this diagram like this. And the d tilde qy is this diagram, and we can deform this diagram like this. Okay. So by this assumption, we have by applying this assumption to these two diagrams, we obtain these equalities. Okay. Oh God. So it is sufficient to prove this equality. Okay. First, we apply the scaling relation to crossing points in Q. Okay. Repeatedly, like this. And at the same time, we apply the scaling relation to the corresponding crossing point in Qx, like this. Finally, we see that the ends of the scaling tree are contained in the following diagrams, like this. And this diagram means the following. For example, this case, this diagram means this diagram. Okay, this case is this, and this is special case, but this means this diagram. Okay, and we can see that this bottom diagram of scaling tree is equivalent to this diagram for any q prime. So we have this completes the proof. Okay. And in a similar way, we can show we can consider the case of gamma pq polynomial p is greater than or equal to 4 case. But there exists a tangle q prime such that this condition. Okay. For example, we choosing this tangle, then the gamma polynomial is not equal to this gamma polynomial. Okay, so we can see that this is not equivalent. So I have a question. If p is greater than or equal to 4, then the gamma pq polynomial distinguishes a mutant knot pair. Okay. But recently I calculated the 4-1 gamma polynomial and 5-1 gamma polynomial, but this invariant cannot distinguish mutant Kinoshita Terasaka and Conway pair. Okay, and I used Kodama's knot program. Okay. これではいいかな。 Okay, that's all. Thank you.